Hi everybody. Welcome to this week's edition of CamLogic's Tech Tuesday. My name is Rob Carver and I'm an applications engineer at CamLogic. Tech Tuesday is our free weekly 30-minute tips and tricks webinar, and today's topic is on machine probing. But first, let's familiarize everyone with CamLogic. CamLogic has been in the CAD/CAM CAE space for over 35 years. And the company was established 16 years ago, initially focused on CAM, servicing mainly the tool and die shops in the area. As the market has evolved, CamLogic has evolved. Interestingly, working our way backward from manufacturing to the conception of the idea or the design. Because we started toward the end of the process and worked our way to the beginning, CamLogic has the fundamental knowledge of what has to be done to assure that each step of the process will result in a product that will actually work or fit into the next phase of development. CamLogic has chosen to represent software and tools that enable our customers to fulfill the full cycle of product development. We consider ourselves integrators and partners for our customers, not just resellers. CamLogic employs a three-legged stool strategy. We partner with Siemens, offering the complete integrated Siemens portfolio for design, machining, analysis and data storage and retrieval. We partner with 3D Systems for 3D printing and rapid prototyping, and Steinbeckler white and blue light scanners, and Creaform for 3D scanning for inspection and quality. Now that you've heard a bit about CamLogic, let's move on to today's topic. On machine probing. And what is it? A machine probe is an electronic tool which fits into a CNC machine spindle. A CNC program drives the probe just like any other machine tool to drive the tip to contact the part in the machine. Either through infrared or radio signals, the point of actual contact is relayed to the CNC machine. Subroutines control the final machine movements, and a variety of probe subroutines allow many different types of probing to take place. NX uses standard Renishaw probe cycles for either Siemens 810D or 840D controllers or the Fanuc 15M controllers. And output variables from the probe will vary from machine tool to machine tool and controller to controller, and the programmer will have to know how to build the logic to manipulate the output. In other words, the programmer must have a basic knowledge of macro programming. Today's focus is going to be on how to define a probe from a solid tool and how to drive the probe in NX. A post-processor with the appropriate code that outputs the Renishaw macros will be required to get the proper NC output. While NX can output either a Siemens or a Fanuc controller, we'll just be working with the Fanuc. And so let's see how this might work. To start with, we need to model up a probe. Here I've got a Cat 50 Renishaw style probe. It's a 6mm probe, and it's just basic modeling, okay? All one solid tool. So the first thing we'd want to do is we want to go in, we're in manufacturing, use just a general CAM setup, okay? Then go into Create Tool. From the type list, select Solid Tool, okay? Highlight the probe. You can either put it in a generic machine location, or if you have a machine simulated or a simulated machine in there, you can run your probe cycles without having a machine. You can run it with a simulated machine, but you can also run it without having a machine. And so give your probe a name. We might call this one Renishaw. Now, let me put it all in caps lock. Renishaw 6, okay, for 6mm probe. Give it an MM so I know what I'm talking about here. Hit OK. Now what we need to do is we have to specify the junction mounting. So this is how it's going to mount into the machine spindle. So we can specify the CSIS, okay, and you have to have the XM pointing along the length of the spindle, okay. And if this is going to be a lathe tool, okay, you need the XY plane should be parallel to the lathe work plane. But for our purposes, all I really care about is having that XC axis pointing up toward along the length of my spindle. Hit OK. Now I need a tracking point. So that needs to be a physical piece of geometry. You can either use the probe, the sphere center, like if you can highlight in here. I've got an actual edge of this extrusion here, or you can have the center point of the datum come up. My quick pick comes up, and I'm just going to pick the center point of my datum. Okay. Specify a stem axis. That's that little guy there. Now the select top face will give me the length of my stem. So I'm going to just select the face of this right here, and that should be okay. If I want to put an adjust register on it, we can add an adjust register number. Go back to tool. I can put a short description in here. 6 millimeter. Oops. Renishaw. Okay. I don't recall the model number of the probe at the time being. You can put that in there if you want to. My material is a ruby. Okay. And now I want to make sure I export this to my tool library. Okay. My holding system, seeing so I'm trying to represent a Cat 50 style holder here. You know, you could model up an HSK 100 or whatever. I'm going to put it in steep taper 50 and hit OK. And it's saving this part file into my tool library, into my graphics folder. Okay, gives me this message. 402-1003 was created in the metric tool library. Okay, and that's pretty much it. So now that I've got my tool defined, okay, I can open up my, actually this is the part I want to open, probe demo. Okay. So basically I just have my MCS coordinate system created. My workpiece is my part here. Okay. And the only extra thing, I think it might be easier for probing purposes to have a set of points out here. It's not necessary, okay, but you know, at times they call out definite datum targets on your blueprints, so you might use that. If you're a little bit on the I don't know, I'm kind of picky, so I like having a nice neat pattern there to probe with. Okay. Basically, it's just like any other setup. We go to probing. We can insert an operation. Go to probing. And you got two options here. You can either do a generic motion or you can do probing. They're very similar. I think last time I used, the last Tech Tuesday I did, it was generic motion I used for gun drilling. This time we're going to use probing. I don't have a tool selected, but we're going to go into our operation. So now we can go in and select our tool, go in our tool library, and instead of going underneath the milling or drilling or turning, we'd go to solid, and then underneath that you have either generic or probe. Hit OK. And now here's the probe that I just created. Here's two other probes that I had created. I'll go ahead and select one of these other ones. They're basically the same thing. If I hit display, you should see it there. Okay. And here you've got probing parameters that you can go into where you can set your standoff distances, your minimum approach, minimum clearance distance, the nominals for the probings. Okay. Your upper and lower. I'll just put some numbers in here just to have something. Okay. If your part is unfinished, you can add some part stock so the machine tool knows when to slow down. Your collision alarm is path obstructed. You have some safe moves automatically generated with the Renishaw probe cycles, and so this would be the alarm that would come up would be collision alarm if it ran into something unexpected. So I'm going to hit OK here, and now we can add a new sub operation. Okay. You've got a variety of options here. Calibrate length, calibrate your stylus, calibrate on the sphere. All probes need to be calibrated at some point before you start using it. I'm just going to assume that my probe's calibrated, but these would be the options that you'd use for calibrating it. I'm going to at first I'm going to do a linear move to a point and specify my point here. Okay. My motion type is traversal. Okay. So now it moves to that point. Okay. So now I'm going to add another series of motions. I'm going to probe. I can either probe a point, probe to a surface, probe a cylinder. I can move to a clearance plane. There's machine control. We're going to use that in a few minutes. I'm just going to probe point, and this is why I say it'd be easier just to have your points already defined. Now we're going to add another unit. And this time I'm going to add the machine control. Okay. And anytime you use a probe cycle, a Renishaw probe cycle, you need to do something with the output. And usually it's through a series of manipulating your variables. In this case, using a FANUC style, I'm going to use #100. I'm going to make that equal to #. Let's see. It helps to have a variable table. In the Renishaw programming book, they have variable tables, and so the variable I want is variable number 142. That's the z-axis error. And so my output comes out here. Hit OK. Now I'm going to go through and I'm just going to now add in a whole series of probing and alternate that with my probing points. I'm sorry, I have a hard time doing two things at once here, talking and running a mouse. And as you see, it steps through for me, okay? Now, one of the things we could do is we could continue to go down through here and add these, alternate it, type in our code each time, but we can also copy this and paste it, and we can come back later and then just edit that, okay? And in this case, I might want it to be 101 because you can't reuse the same variable all the time. You want to be able to manipulate this output. Okay. Now we're going to add another probing. Pick my next spot. And eventually we're going to build this entire probing path here, okay? And again, copy and paste that and edit it and just change my increment my variable up by 1, okay? So that's the general idea. If I wanted to go in and probe a cylinder, which we're going to do eventually, okay? I want to probe a cylinder. Now here I would select the face, depth. Give it. It's an internal cycle because I want to probe the inside of it. If I were probing a boss, I'd have an external cycle, okay? And instead of midpoint, I don't want to reach down in there to the depth there. I might risk having a crash or something. So I'm just going to specify a depth and give it, I'll say 20 millimeters in depth, and specify my angles. Now I did find out one thing, having a negative angle in there kind of gave me an error previously, so I want a positive angle in there, all right? And the error didn't occur until I posted out the program. So now it's going to go through and it's going to drop down into that bore. And the basic idea is maybe we're trying to set up a coordinate system. So maybe we probe those surfaces and on the machine instead of 0 and in Z, and then come back in and probe that cylinder as my XY reference and set a coordinate system. Or maybe we're doing a little bit of on-machine instruction and inspection here. There's print outputs. You can output upper and lower tolerances. All kinds of different things, okay? And if we wanted to simulate this, what we've got so far, reset it to the beginning, simulate this, have it go down through, probe our points, okay? Generate it, okay, and hit OK. Now I've got another probe cycle here that I did. Just going to replay that. I'll go in and edit it, okay, and use the animation inside the utility here. So like I said, you can go through, have predefined points. I think that's the easiest way of doing it myself. Might make the program run a little bit neater, but you can choose beforehand where you want to probe it. But you can probe on any surface. I mean, you don't have to be anal like I am and use predefined points. And I'm going to come back. I'm going to generate this, and I just want to show you what the output might be for that. So I'm going to post this, and I've got a probing cycle. Now your post is going to have the proper code to output the Renishaw probe cycles. We're not going to get into that. Let me drag that onto my window here. But you can see how the code outputs the positioning. It outputs the 9811, which is a probe move. Then this is the output for it, and then each subsequent move after that is a 9810, which is a protected move to the position. Then it goes to the into the 9811 probe routine. And what you would want to do is insert this code, the 100 equals 142, in behind each one of these 9811 probe routines. And then later on, you do some manipulation with those, either averaging them all together and setting your coordinate system equal to that average, or correcting your coordinate system by that average. Here, this is the 9814. This is the diameter that's spit out, and this is the X position, Y position, and this would be the diameter output. So there's a wide variety of different things that you can do with this, and this is the basics, the building blocks of trying to get the code to start working for you. The advantages of having on-machine probing is, rather than having your operator try to set up each individual job, as long as your fixturing is good enough where the probe can get into the different features, the machine itself can pick up its own coordinate systems and update its fixture offsets and start to program. Where I used to work, we did this all the time. It's a huge time saving, and it eliminates a lot of human errors, reading indicators, and mitigates some of the differences in skill levels between operators. So that's pretty much the conclusion of my demo, and we will continue on with our presentation. So getting back, we can't really emphasize enough the importance of training to get the most out of today's technology. This type of use of the software, it takes a little bit of time, and it takes a little bit of investment in employee training to get the most out of it. It's well documented that training helps improve the speed of use, and it increases the efficiency. It provides faster problem solving and leads to fewer support calls, and that all positively affects the company's productivity, the return on investment, and eventually the bottom line. At CamLogic, we offer a wide variety of hands-on, instruction-intensive courses for users at every level. Training is available at the on-site location of your choice or at one of our training labs located throughout the Midwest. For more information or to register, please visit our website. And today's webinar can be found on YouTube, usually within 24 hours of the broadcast. Check out CamLogic on YouTube for past webinars as well. And you can visit our site at www.camlogic.com. We can be found on LinkedIn, Blogger, Facebook, and Twitter. And thank you for joining us today. And if you have any questions, please feel free to call or email me at any time. And you have a great day.